We are in the third part of the ALCN reasoning. So what we are doing gradually throughout the videos, we're trying to gather the ingredients for designing the algorithm for ALCN reasoning. Here is another ingredient. So up till now, we haven't considered the different kinds of number restrictions together and exactly what we'll be doing to start with, right? So let us consider a concept expression which is C0, which contains less than equal to R or no, let's say HC. And greater than equal to 2HC. So what I'm saying that the person has got at most one child, but the next time you are saying the person has got at least two children, which is infeasible, right? And we need to see whether we can sort out some way to prove this, that it is not possible, right? I know this is a very trivial example, but this will be enough to make our point, right? And very important ingredient of the algorithm, right? So as before, we'll start with the assumption that there exists an individual that belongs to the class C0, and very customarily we'll be applying the intersection rule, right? Now if we apply the intersection rule, you'll be having C0 here less than 1 HC greater than 2 HC, right? Now we cannot apply this rule first because this assumes that there should be at least one child, right? But in order to make it to be true, I can add two children, right? Two children of A, right? So this is what we'll be doing here. A C0 less than equal to 1 HC greater than equal to 2 HC, and we'll be adding two children HC B. And what will be the class level for B? Nothing, right? Because I'm not saying that the child should be belonging to a particular category. That is not in my specification, so I can leave that part. We are doing a very minimalistic design. And HC, you can have another individual which again will not belong to, don't bother to make it belong to any class, right? Now additionally you have to do something else, otherwise this will not hold true. What is the condition this will not hold to, even in spite of having this B and C to be two children of A? If B and C are equal or same, right? So we need to impose new constraints to make this to be true. So what is the new constraint? B not equal to C and C not equal to B, right? Now let us try to apply this. Now if we try to apply this, we see that though I am saying that A has at most one child, but already it is having two children, but these two are not the same. They are not referring to the same entity. So in that case, this will be an example of clash. So till now we have considered two class conditions, right? Condition 1 was that this bottom class is a part of a class expression in any of the nodes. So this is the condition 1. Condition 2 is both C and negation C is in the is one at least one of the they are the levels of at least one of the nodes together, right? Now we have got the third condition, right? But before going to the third condition, let us try to name this with something which we'll be using later, and that particular name is or that particular um, property is called identifiability property or identifiable. Identifiable. So let us define what do we mean by identifiable. So let us define identifiable nodes. So if we need to consider two nodes. So two nodes x and y are identifiable given a tableau state. So it should be defined based on a tableau state, of course. In a tableau state, say let us name it to be st. If st does not contain this and this, in that case they are identifiable. Otherwise x and y are identifiable. Sorry, it will be non-identifiable. Or distinct. So here B and C, they are not identifiable, they are distinct, right? So my new class condition, the third class condition would be if you have this expression less than or equal to n r and x is a member of this and x has n plus 1 r successors. R successor is basically if you have say a node x which has got a successor say y having relation r, right? Successors with no two nodes are identifiable. So you can see that P and C, these are the only two nodes. They are not identifiable and you have got this. So this is a class. So now on we will be considering these three classes, right? Any one of these class condition, and this particular class condition is used to accommodate the n part of ALCN, right? Now I guess we have got all the ingredients that we need to have with us to start designing the algorithm formally, right? So there are certain prerequisite things that we need to consider. So the first Tableau algorithm that we are considering, that is the ALCN Tableau algorithm for empty boxes. So you know what we mean by empty boxes, right? T boxes is basically the uh, generalized class inclusion axiom, is a set of generalized class inclusion axioms, and that part is empty. We have only the query. That is what we have in our uh, mm, system, which we need to prove or disprove, right? Now what is the prerequisite? The prerequisite that is that every concept expression should be in its equivalent negative normal form. Right. And what is that? So an expression that will be designated as to be in NNF if it contains negation only in front of the atomic concepts. Right. So let us see different expressions and try to see what would be their corresponding NNF representation. If we have a negation of C, this is equivalent to C. Very intuitive to follow, right? Negation of C intersect D would be equivalent to C. So this is a De Morgan's equivalent in description logic. And if you have negation of C union D, it will be negation of C intersection negation of D. If you have negation of there exists RC, the negation would be for all R not C. If you have negation of for all RC, that is equivalent to there exists R negation C. Negation of less than equal to NR, so this is the utmost restriction, is equivalent to greater than equal to MR, where M is equal to N plus 1, right? I am making it greater than N plus 1, right? And the other is greater than equal to NR, right? So it will be equivalent to less than equal to, so I am converting the at least restriction expression to at most one, right? R, where N equal to N minus 1, and this is for N greater than 1, right? Now if N is equal to 1, M becomes 0, which is not there in your concept expression. It's not a valid concept expression. So we have to handle that case differently, right? How do we handle that case? So negation of greater than equal to 1R. So this is the special case, right? This is equivalent to, so what I'm trying to say here, that it is not the case that A has greater than or equal to 1R successor, right? So that means A does not have any R successor, right? And that we can write simply by saying R dot bottom class. So this means that a particular concept expression which is a member of this class does not have any R successor, right? So this is how we can convert a given complex expression into its corresponding negated normal form simply by pushing the negation symbol to the to in front of the atomic concepts only, right? Now coming to the algorithm. So what is your input? Input is a concept C, and C is an arbitrary concept in NNF, right? And what a Tableau state will contain? Let me first give you uh, informal description of this Tableau state. Perhaps you know already what will be there, right? So this Tableau algorithm which we are talking about, so this Tableau algorithm maintains a set of Tableau state, right? Now each state will contain two things. One is a Tableau graph. Till now we were naming it as the interpretation graph, right? And the second thing which we just got to know, that there would be a set of inequalities. This is not really there for there in every Tableau state, right? There are some certain special Tableau states where these inequalities will be there just to indicate whether a pair of individuals are non-identifiable or not, right? So let us now focus on the Tableau graph, right? So we just need to know or define or give a formal definition of the Tableau graph for a concept C. Tableau graph for C. So it's a directed graph. We have seen, right? The edge flows from a node to another node. So it's a directed graph set of vertices, set of edges, and a set of mapping functions, right? So V is a set of vertices, edges, and L is a function that assigns labels to each node and edge. So this is that's why it's called a label function. right? Now this level function has got two variants, one for the nodes and the other for the edges. So for a node, say x belongs to V, we can have a mapping of this uh, x, right? So this L function is mapping x to a set of class expressions, right? So this will be a subset of the sub expressions or sub concept of C. I'll come to what is sub concept of C formally, but informally, if you can see, if we can go back to the earlier examples, you can see, for example, A is a member of C. So A has a level called C0. Now C0 has got many sub expressions, like for there exists HC, M, there exists HCP. So these are sub expressions of C0. So these are subs of C0. And A is also a member of this. A is also a member of this. So these are called the sub expressions. And the level set of A, that is L of A, is C0 as well as the subs of C0. And that's where the concept of sub expressions came while we are talking about, or we are defining the mapping function of the nodes, right? And for every edge xy belonging to E, the L xy will be equal to R, right? And what is R? Which connects x to y, right? Now let us define the idea of sub-concept more formally. So the idea of sub-concept. Now we have seen earlier that if you take every node in a Tableau graph, so the level of that node is a sub-concept of the root node, sub-concept of the concept in the root node. So we had in the earlier example, so A had a level C0, right? Now let's say you had say B, and B is having say M as a sub concept, or level to be M, and not M, not P. So these are the levels of B. Now all these are sub concept of C0, right? So that means that this sub concept has a recursive sense in its definition, right? And that recursive sense is being used to define it formally. Now to start with, if we have an atomic concept, say A, the sub concept of A will be A itself. So when A is an atomic concept. So this is your base condition of your recursion, right? Now what will be the sub of not C? Sub of not C will be not of C union sub of C. and if C is an atomic, then it will be C itself, but C can be a complex expression. Now sub of C intersection D will have C intersection D union sub of C and union sub of D. The sub of C or D is equal to C or D, the expression itself, union sub of C union sub of D, right? Sub of there exists RC, it will have the same expression as the sub concept. Additionally, it will be having this to be sub concept as well. Now sub of for all RC similarly will have this and sub of C, right? What will be the sub of greater than equal to NR? This expression, of course. Will there be anything else? No, because it does not concern any other class expressions, right? Similarly, sub of less than NR, it will be less than NR, right? Now, the Tableau state or Tableau state T will have what? This Tableau graph which we have discussed earlier, and this Tableau graph consists of V, E and the label mapping function and the set of identifiers, right, or inequality. So this is a set of inequalities, right? We have defined the class conditions, but again for the sake of completeness, let us write the class conditions again. So the first condition is that this bottom concept belongs to the label set of X. X is a node in your Tableau graph. Tableau state. So this is a node in a particular Tableau state. C and negation C, this particular set, both of them, they belong to LX. So this condition, or the third condition is that less than equal to N, it belongs to the LX and X has N plus 1 R successors with no two of which can be identified. Now coming to the core of the algorithm. So the Tableau algorithm. We'll be doing or mentioning the steps as we have done in the examples, right? So what is your input? Input is a concept expression. Take any C. In our example case, that was C0, right? And output is either satisfiable, either the concept is satisfiable or unsatisfiable. And additionally, we can ask for relevant interpretation. Right. Now, this algorithm can be divided into three distinct steps. One is, the first step is initialization. The first step is initialization. Now what we will do in the initialization, we define the initial tableau state, right? So our initial tableau state, we denote it as T0C because it is with respect to the input concept C. It will have again the set of vertices, and what would be that? A single node, single individual represented as a node. In our example, that was A, but here with the to follow the notion, we are using x0. We can use anything here, x0. The set of edges empty because we have we just say that x0 is having C. That's it. We don't have any edges, right? You have a mapping function L0. We'll define this later, and the set of identifiables or inequalities to be again empty. What would be your L0? How do you define it? Because we have got only one node x0, it will be C, right? And we don't have any L0 for edges because the set of edges is empty, and you are maintaining the set of states S. You will include this tableau state in the set of states. So this S is a set of states that your Tableau algorithm will be maintaining, right? The second step is the iteration step. So we are into the iteration step, and what would be our task here? Very simple. So while we were working with the examples, if you remember the edges in the whole construction, they were talking about different rules like say at-most rules, union rule, intersection rule. So this assumes that there is a set of rules that governs the entire algorithm. So there is a set of inference rules which governs this iteration, right? So in this iteration, what we will be doing, and each rule here has got two parts. One is any rule, so one antecedent and one consequent, right? And this antecedent is called a precondition. If this condition is satisfied, then you can apply this rule, and if you apply this rule, you will arrive at a post condition. You will arrive at a post condition, right? So what we'll do, we'll pick up the rules from the rule base and iteratively apply them, right? So iteratively apply rules of the form, the precondition, so this precondition should be matched in order to apply this rule, right? And the post condition. Post condition will impose some changes in the Tableau state, right? So we'll arrive at a new Tableau state, right? Let's assume that this new Tableau state is ST, right? So what we will do with this rule set? First, we'll choose our Tableau state. T from this S. This S is a set of Tableau states which we are maintaining, and this T should be class free and not complete. So if the Tableau state T is class free, then there is no point of applying the rule, because I know that I have arrived at a class. And if the Tableau state is complete, we cannot apply any rule, even if we want to, right? Now, second, we select an arbitrary rule. Select an arbitrary rule and an arbitrary node in T, right? But we need to check whether given that precondition satisfied with precondition of the rule is satisfied. If this is so, we do Tableau transformation. Now, what kind of transformation we are talking about? So your set of state will be changed. So was your set of state before applying the rule. Now this new state will be removed because you are picking it up from the set of states, and you will be adding the resulting Tableau state, right? And you will be doing it iteratively, right, until you reach the termination condition, right? And that brings us to the termination stage of the algorithm. So termination. So already we know that what kind of conditions that we are looking forward to while we are talking about termination, right? So the first condition says that if all the elements in S contain a clash. So this is one condition. The second condition is if S contain a Tableau state which is class free and complete. So we are looking forward to the completeness of the Tableau state and class. So these are the two things we are uh, will be probing to arrive at the termination condition, termination of our algorithm, right? But these two different conditions will give us two different outcomes. Now, can you guess what kind of outcome it will give us? So, if all the elements in S contain a clash, so that will tell us that this particular concept C is unsatisfiable. And what kind of condition, what kind of outcome we will have if this condition is satisfied? So, we will say that C is satisfiable. And you can look back that these are these are the things exactly you have done in our examples, right? So we had an example of this and this as well, right? So with this, let us stop for now. In the next video, we will talk about, I think the core of this algorithm is the set of rules, which we have talked about in informal term, but we will like to define them in formally, and we'll do this in the next video. Thank you.